Okay. If you're ready, we can start as well if you want. Uh, Welcome, everyone. Thank you very much for accepting to give us this talk. We have today Kiril Maltsev from MPIA. If you're ready, we can start as well if you want.
Yeah. So thank you very much to the organizers for the opportunity to present some of my research here, and also in particular to Seval Tashdemir for establishing the link while I was visiting Istanbul last year, which was a very nice opportunity to also visit the Istanbul University Observatory. So I have good memories of this
Cool. When
encounters.
was that?
That was last year in September.
Oh, okay,
September.
cool. Very nice. Very
I
nice.
was just for private reasons in Istanbul to attend the wedding, and that's how
All
we
right.
also met
Okay.
again, and that's how it all came
All
about.
right. Cool. Thank you very much.
So yeah, I've prepared a talk, and I hope that it will be interesting for you, and perhaps there will be some interactions, and I'm very open for discussions. So it is about the final fate of landscape of massive single and binary strip stars. And I'll be referring to papers, one of which I'm first authoring, and another one where I'm co-author that relate to this subject. And to give you an overview of what is to come, I would like to first give a broad overview into core collapse supernovae, then talk about explodability measures that discriminate final fate outcomes, which is successful or unsuccessful explosions. And then see what is the application of these measures to predict the final fates of massive star evolution. And finally, look at observational indications of black hole formation. So I think a nice comparison is that between the single star evolution of a sun-like star and a massive star. So a sun-like star evolves on a timescale of about 10 gigayears, right, and ends up its evolution with the white dwarf remnant. Whereas a massive star, and by that I mean a star that at the end of its evolution develops an iron-rich core that then collapses. So these stars evolve on a much faster timescale. So a late B-type star, for instance, only gets about 100 million years old, and earlier type stars even get younger at the time when they die. And these stars are obtained at zero H sequence masses of about 8 solar masses when considering only single star evolution models, but that changes with binarity and metallicity, of course. After the main sequence evolution, they evolve into some giant phase, and eventually at the end of their evolution either explode as a supernova or end their life without an explosion, as we shall see. And so this talk will be much about the neutrino heating supernova mechanism, and that's why I wanted to dig out the original paper from Colgate and White from 1965 that introduces this concept of this supernova mechanism. And I would like to read out the abstract. It's quite brief, and I think it conveys the essential idea. We regard the release of gravitational energy attending a dynamical change in configuration to be the primary energy source in supernovae explosions. Although we were initially inspired by and agree in detail with the mechanism for initiating gravitational instability proposed by Burbidge et al., we find that the dynamical implosion is so violent that an energy many times greater than the available thermonuclear energy is released from the star's core and transferred to the star's mantle in a supernova explosion. The energy released corresponds to the change in gravitational potential of the unstable imploding core. This transfer of energy takes place by the emission and deposition of neutrinos. So the detail is quite complicated and involved to understand the mechanism. But I think I would argue the basic idea is quite simple to grasp. And to help understanding, I would like to give a quite simple intuitive example. So think of a two-body collision, for example, when one claps one hands. So this is basically an excess of energy that when the hands clap, that is transformed into some internal energy, and we feel the heat in our hands. And now consider the case of a collapsing iron core. After the core silicon burning phase in the stars, and the nuclear fuel is depleted and the iron core falls in. So that is something like a gravity bomb. There is an enormous amount of gravitational binding energy release. And the question now is, where does this energy go into? And as in the abstract is mentioned, a leading idea initially was that it is transformed into thermonuclear reactions that then power supernova explosions by nuclear reactions. But what Colgate and White propose is another mechanism. It is that the dominant part of the gravitational binding energy is transformed not into the ordinary heat, but into neutrinos. And the fascinating, as I find, thing about it is that more than 99% of these neutrinos actually leave the star because they are hardly interacting with the matter. But because the matter is so dense in the collapsing iron core, there is some interaction of the neutrinos with the collapsing matter, which then deposit energy and drive the explosion. And this is what is illustrated on this figure from this original paper. We basically look deep into the star. So on the y-axis, we have the radius of the star, and on the x-axis, the time. And you see here sketched the evolution of a collapsing Mars shell, then reaches a certain region in between 10 and 100 kilometers away from the center, where a neutrino deposition takes place, neutrino energy deposition. And that then eventually drives an expanding shock wave that is reversed in this direction. So it's not anymore imploding, but exploding. And I shall explain on this next slide in more detail how this comes about. So the idea is to understand how one can get from the implosion of an iron core to the explosion of the stellar mantle. And again, an initial setup is the iron core, which collapses after the core silicon burning phase. The inner core of the iron core collapses faster until nuclear densities are reached, and a proto-neutron star gets formed in the very innermost vicinity. The outer infalling layers bounce off this proto-neutron star such that a shock wave is generated, an outwardly generated shock wave. But this shock wave has to propagate against the ram pressure of the accreting infalling matter, and also due to the high temperatures involved, is subject to photodisintegration of the heavy nuclei, and that's why it stalls. It stagnates. So it basically stays where it is at a certain mass shell, about 100 kilometers away from the center. And now comes the interplay of the neutrinos with the matter. So so just above the proto-neutron star, the neutrino cooling dominates, which means that the neutrinos actually take away internal energy, whereas near the base of the shock, there is the so-called gain region. In this gain region, the neutrino heating dominates, which is the neutrinos get trapped. They cannot really escape the star because of the high densities and neutrino opacities, and they transfer the energy to the shock, which then is revived, and as you can see here sketched, and drives the expansion of the shock wave that then unbinds the outer layers and shock compresses matter to initiate explosive nuclear burning and unbind the star and leave behind the proto-neutron star. So now we have an idea of the neutrino-driven supernova mechanism. But do all massive stars explode by these mechanisms? So I will be mentioning here two arguments against it. And the first is that there is a large discrepancy between the observed supernova rate and the star formation rate. It is presented in the paper by Horiuchi et al. 2011. And you see basically the cosmic supernova rate measurements as a function of redshift and theoretical predictions by emanating from the measured cosmic star formation rate. And you see the discrepancy here that is preserved across the redshift, where the cosmic star formation rate based prediction of the supernova rates is higher than the one that's actually observed, right? And so one immediate sort of proposed solutions to this is that as an important fraction of the massive stars do not explode in supernovae. And the second argument comes more from the theoretical side, and that some three-dimensional simulations of core collapse supernovae, so the most detailed way of that we currently know to understand this complex phenomena with detailed input physics, are non-exploding. So despite evolution of the simulation over seconds, there is no revival of the shock. And that what is inspiring the explodability measures to discriminate the final fates, that is successful and unsuccessful explosions. And if you basically look back about 20 years ago, there was quite the idea of a quite smooth change in compact remnant type with increasing initial mass, with modulations due to metallicity and but overall as a function of initial mass, the helium core mass at the end of the evolution would grow rather monotonically, and one would have a smooth transition from a neutron star, black hole formation by fallback, and then eventually direct collapse black holes until one reaches a window of pair instability supernovae, leaving no remnant behind, and again then a window of failed explosions preceding black hole formation. So that is for a long time the leading idea. And that got revised over the course of the last 15 years quite substantially. So one important development was the formulation of the so-called compactness criterion, which looks at the mass to radius relation at a fixed mass coordinate at the time of the core bounce, or similarly at the time of the outset of our iron core infall. So and one typically chooses the mass coordinate of 2.5 solar masses enclosed, and then the idea is the following: less compact cores, they are more likely exploding, whereas highly compact cores lead to failed supernovae and black hole formation. And applying this criterion to different stellar evolution sets, which you see enumerated here with different acronyms at variable metallicity, then gives quite well, some have this rather monotonic transitions, but some have these islands of failed supernovae here and here again, and some have even predict successful explosions over quite the entire mass range with different mass fractions of black hole formation that would depend on metallicity and stellar evolution sets. So that was the criterion introduced by O'Connor and Ott in 2011. But later, investigations have found that there is no single threshold in the compactness value that would allow us to discriminate the final fate. So, and that inspired the authors to proceed first to improve it in several ways. First, to map out the mass coordinate at which there is a steep density decline, not by a fixed mass coordinate of 2.5 solar masses, by fix it by an entropy condition. Here, where the entropy per nucleon number is equal to 4. And then look at the mass gradient at this location. So this is the mu4 variable. And then, so is the argument, compare it to a proxy for the neutrino luminosity. Because theory by Burroughs et al. From the 70s has shown that there is a minimal neutrino luminosity that is required for achieving a successful explosions. So stars that do not have a sufficiently luminous neutrino burst after the formation of the proto-neutron star, they fail to explode. And those that have a high enough neutrino luminosity, they do succeed to explode. But this critical value is a function of the mass accretion rate. So the higher is the mass accretion rate, which favors a failed explosion and black hole formation, the higher must be the neutrino luminosity to compensate for that. So that is the theory. And then by construction from these two variables, the authors have found proxies for these two variables. So basically, they set the gradient in relation to the mass accretion rate and the neutrino luminosity as in terms of these two variables by analytical considerations. And then what they find phenomenologically by comparison to a large sample of stellar evolution models is that there is a simple separation line through this plane that dissects successful and unsuccessful explosions. So that's the parameter from Ertel et al. From 2016. Now, in our work, we have found a two-parameter criterion for classifying explodability not being sufficient to discriminate the final fates. So we have probed different two-parameter criterions, the one introduced by Ethel, based on mu4, m4, and mu4, and also the compactness criterion, in addition with the central entropy-based condition, and found that only when these two conditions are applied in concert with threshold values in both compactness and entropy, as well as in the mu4 m4 variable, only when these four variables are considered in concert, this allows to achieve higher accuracy predictions of the final fates. So when these criteria are applied in concert, more than 99% agreement with the outcomes of a semi-analytical supernova model evaluated over nearly 4,000 stellar evolution model at the onset of iron core infall is achieved. So each of these dots here correspond to a stellar model at the onset of iron core infall, and the colors are the predictions made by a semi-analytical supernova code. And now, okay, this is based on 1D simulations, all these mappings of these criteria. How about the comparison to 3D simulations? And this is a comparison that we have done in the paper, and we find that the compactness criterion achieves a similar accuracy as our multi-parameter criterion. So indeed, it is indeed the case that less compact stars are prone to an explosion, whereas highly compact stars are more likely resulting in failed explosions. And we also find some evidence for our way of parameterizing the explodability in the parameter space spent by the mu4 m4 variable and the mu4 variable, which proxies for the mass gradient and the neutrino luminosity. So let's apply these criteria to the final fates of massive star evolution. And the most OB-type stars are actually not evolving as single stars, but are subject to interactions with binary companions. And an important outcome of these binary interactions is envelope stripping by binary mass transfer. Whereas the more massive star, which evolves faster, expands into a giant phase sooner than the companion star, and therefore overfills its Roche lobe if it's close enough to the binary companion, which then initiates a binary mass transfer. So the more massive star acts as a donor of its hydrogen-rich envelope to give it to the less massive star initially, which then becomes an accretor star. So that is an often found scenario in a massive binary star evolution. So that then leaves behind, to give you an example, a stripped star and an accretor star. And if that stripped star then becomes a black hole, and eventually at the end of its evolution, and then there is a second episode of mass transfer that may evolve from there. That comes about when the secondary star expands, and the expansion may lead into the common envelope evolution, where both the core of the secondary star and the black hole are engulfed by a common envelope, or a stable mass transfer, where the black hole accretes the envelope material from the expanding secondary star. But the outcome of this is, in the case of a successful common envelope ejection, and in which basically where there is no stellar merger, in other words. And here, when the entirety of the envelope mass is accreted onto the black hole, that then leaves behind two cores that are much closer than initially, and then allows for binary black hole mergers. So this is an idea that we will look into later as well. And there are also different classifications of the mass transfer depending on when it takes place. So whether it takes place on the main sequence, these are case A mass transfer phases. Case B is in between the end of the main sequence and the end of coherent burning, and case C is after the end of coherent burning. And something that we have found is, by comparison to stellar evolution models, is that the outcomes of massive stars are correlating with bonds in CO core mass, the carbon-oxygen core mass of stars, which is formed at the end of coherent burning. And therefore, as we argue, the basic final fate landscape resulting from massive single and binary strip stars, which are compared here, are already seeded at the end of coherent burning. And this is what you can see here from these pre-supernova parameters, such as compactness, central entropy, and the mu4 m4 variable, as a function of CO core mass for all these stellar models. And you see these peaks developing, where one reaches the regions for which black hole formation from failed explosions would be predicted. Here, these are reached here, and these are reached here. And the brown shaded areas show the regions of failed supernovae as predicted by our criteria, whereas the yellow shaded regions predict successful explosion areas. And white regions are unclassified, so basically based on this parameter alone. So one needs to look into other parameters. So this is what we have done in terms of the method, and this is the outcome. So basically, evaluating the criteria, we get this central result, and I think this is perhaps the main message and the result I would like to convey in this talk. This final fate landscape of single stars and binary strip stars. So we see on the x-axis the carbon-oxygen core mass of stars developing at the end of cohelium burning. And on the y-axis, the metallicity, and color-coded is the compact remnant type predicted for single-star progenitors and case B donors, which are strip stars, such as those on the example discussed. And first of all, there is a bimodal black hole formation landscape, which is there is a window in CO core mass in between about 6 and 7, or and 7 and 8. So for single stars between 6 and 7, and for case B donors between 7 and 8, roughly, where failed explosions occur. Then there's quite a wide window of successful explosions, which either leave behind a neutron star or a fallback black hole. And then the onset of a plateau of black hole formation outcomes extending through all the high mass range up to the parent stability mass gap. So this is the prediction of the model. Okay, and what is important here apart from this bimodality? It is that the case B donors have a shift of this failed supernova window towards higher CO core masses compared to the single stars. And in addition, there's a modulation with metallicity. So higher metallicity also shifts the these failed supernova windows towards higher CO core masses. And what does that mean? So basically, that means that the production of black holes from strip stars is much less frequent and efficient than from single stars, just because of this shift and because of the IMF. If you think of the zero-H mid-sequence mass of stars and the relation to the carbon-oxygen core mass, look at here the single star models from Schneider et al. 2021, S21 at solar metallicity in Turkey. So these are here, okay, and the corresponding case B donor CO core mass to Zam's mass evolution. So this is in blue. So the same reference values are reached at much higher zero-H mid-sequence masses for the strip stars. So in addition to this difference in CO core mass to Zam's mass relation and these shifts, this makes black hole formation from strip stars quite a rare process. And we will come to that later. It will be important in the context of gravitational wave astronomy that I will come to eventually. But first, I would like to comment why this is so. Why do we have this bimodality? And this is explained in a separate paper to which we also make reference and sketched here. So it's quite involved, and I would like to basically I will try to convey you these complex ideas. So think of the core carbon burning phase and a certain amount of carbon fuel. And now consider the burning front, so the carbon burning front, and how far it can propagate during the core carbon burning phase before the effective Chandrasekhar mass is reached for the collapse of the core to initiate the core neon burning. So if there's a high amount of nuclear fuel, then the carbon burning front does not propagate far and stays well below the effective Chandrasekhar mass for the collapse to the next burning stage. Now, if there's a moderate amount of the nuclear fuel, it actually has to propagate further to compensate for the basically to compensate for the outward energy losses due to radiation in neutrino emission, such that it basically comes as close as can be to the effective Chandrasekhar mass. Consider this scenario. So it's staying below the effective Chandrasekhar mass, but is quite far out. So this leaves behind quite a massive carbon-free core, which later leads to, because of subsequent burning phases, to a massive silicon burning core, and eventually a massive iron core and a highly compact core. So this is the case when one has the peak in the compactness and iron core mass of the stars, which then correlates to failed explosions. So this region 2 correlates with failed explosions. So, and this is what basically the first band in the black hole formation as a function of zero core mass. But now, why does it go down again as the core mass increases? This is because of the following. With a lower amount of fuel, the burning front propagates even further, such that it surpasses the effective Chandrasekhar mass for the core neon burning phase, which means that core neon burning is ignited even before the core carbon is depleted. And that then basically stops the further expansion of the core carbon burning shell that leaves behind a less massive silicon core at the end of the evolution, and therefore a less massive iron core and compactness, lower compactness. And this is why we have the decline in the phase. So I hope this was clear. We can also discuss later. Okay, and now an additional modulation that comes about due to the binary interactions, and this has been the result from our work. Now, when hydrogen-rich envelope stripping or higher metallicity is in place, then more mass is lost from the hydrogen burning shell. When more mass from the hydrogen burning shell is lost, then the helium core mass is less massive. And during the cohelium burning phase, this leads to lower core helium burning temperatures, and the triple alpha reaction is basically taking place. But the carbon 12 alpha reaction, basically the triple alpha reaction producing carbon, and the carbon then capturing alpha particles to create oxygen, that takes place later because of the lower core temperatures. And because of these lower core temperatures and later onset of this carbon alpha reaction, there's a higher carbon abundance at the end of this coherent burning phase. And with the higher carbon abundance, there's this shift towards higher carbon oxygen core masses for this supernova black hole transition, basically this region 2 that I just described, because the carbon abundance controls the amount of nuclear fuel, whereas the carbon oxygen core mass, it controls the neutrino luminosity, basically the neutrino cooling in the core. And this is why there are these shifts as well in between the single stars and strip stars, because of these interactions and the differences in the carbon abundance for the fixed carbon oxygen core mass, as you can see sketched here. Okay, so now let's put that in comparison. So with other models. So the model that we have constructed is not the first one on the market, so to say, to predict the final fates of massive stars as a function of carbon oxygen core mass, and there are plenty of other ones listed here. And they all predict, as you see color-coded here, different remnant types. For example, yellow neutron star, red neutron star or a fall black hole, brown a fall black hole guaranteed, and black a direct collapse black hole as a function of carbon oxygen core mass. Okay, and what is strikingly different from our in our parameterization compared to the previous models is that we have this bimodality with the wide window of successful explosions, which other models don't predict, and also a wider window of successful explosions towards higher carbon oxygen core mass. So as you can see from this plot, 11 solar mass cores carbon oxygen cores would still be predicted to explode in our framework. And we compare it to the most luminous type 2 supernovae, a failed supernova candidates, a type 2 N supernova, which likely is of a single star or origin, and type 2b, 1b supernovae, the most luminous ones, and the type 1c supernova. And what we get is that while the most luminous type 2 supernovae allow us to estimate their carbon oxygen core masses, first of all, and I'll get to that later. But because of the high uncertainty, it's quite a shaky inference here. So it does not really allow us to obtain stringent constraints on the compact remnant model. Many of them would predict these stars to explode anyway. But what we get is from the type 1c supernova 2011 BM, we get an ejecta mass in between about 8 and 7 and 17 solar masses, which then sits into the type 1c supernova, and we make a minimal assumption about the proto-neutron star mass, would have to have a progenitor carbon oxygen core mass of at least 8 solar masses. And many models are already excluded by this observation. So this is what we find based on electromagnetic observations. Okay, I have a little time left, but I'm nearly at the end. And the final part of the talk will lead with observational indications of black hole formation. So I would like to motivate and report on the so-called missing red supergiant problem. This is on an observational, basically a finding that there's a lack of high luminosity red supergiant progenitor observations of type 2 supernovae by direct imaging. So you see here on the x-axis the luminosity from 4.6 to 5.6 dex of red supergiants in the large Magellanic Cloud, the small Magellanic Cloud, and M31 and M33. So these are just observations of red supergiants generally. Okay, so and these basically have a cumulative distribution that follows these trends. So there's an upper bound, basically the Humphrey-Davidson limit for these red supergiants, up to which they basically stretch out. And now this turquoise curve shows the cumulative distribution of imaged progenitors of type 2p supernovae, which are red supergiants. And as you can see, they don't reach as high. First of all, they more slowly increase from 4.8 onwards, and they only reach basically a limiting luminosity of about 5.1. So there is no direct imaging progenitor of a type 2 supernovae more luminous than 5.1 dex. In contrast to observations which would allow the parameter space for red supergiants to stretch up to 5.6 index. So why do we not observe them? So that's the question that is raised. And it has been proposed that some of these stars do not explode. Some of these red supergiants that reach this luminosity, and instead they form black holes quietly. And this basically this idea or picture is corroborated by a recent observation of a fading luminous star in this range, basically in this luminosity range, that was basically having a luminosity of, I think, of 5.3 or so dex, and then faded in the optical. Basically a disappearing star. Basically the best failed supernova candidate that we have so far. So what do we find in relation to this work? We find that our modeling, as you can see here on the carbon oxygen core mass, based on the carbon oxygen core mass, we predict these bands in failed explosions. okay? And the carbon-oxygen core mass can be related to the pre-supernova luminosity of stellar progenitors. And these shaky values here, basically they represent the most luminous type 2p supernova progenitors, and the yellow points are dots from simulations. And our modeling would predict the failed supernova exactly in this region where was the observation of the failed supernova candidate, this N6946BH1. So it's matching very well our predictions, and it is to stress, it's in exactly this band in between. So here I take an even optimistic picture of the missing red supergiant problem. So it's within the band over which the red supergiants are missing as type 2p progenitors. Something that we also find that failed supernovae can only partially address the missing red supergiant problem, according to our modeling of and explodability criteria. Here is a plot showing, as a function of carbon-oxygen core mass and central carbon abundance, the final fates color-coded. So basically, black regions correspond to failed supernovae, and the colored lines show different stellar evolution models passing through this region, and in the red dashed lines show the carbon-oxygen core masses of the range, basically, over which that encapsulates the luminosities of the missing red supergiants as type 2p supernova progenitors. And for none of the modeling choices, we can completely fill basically the region in between these red dashed lines. So in other words, the missing red supergiant problem can only partially addressed by failed supernovae. This is what you find. So it can be addressed, but only partially. So what to take away from this? Either this is the case, so either the missing red supergiant problem has to be addressed also by other explanations different from a failed supernova, or our modeling of failed supernovae is too pessimistic. So basically, it's an indication that our modeling is basically too not producing enough failed explosions. So it's either the one or the two. And so now this is another indication of failed supernovae coming from the masses in the stellar graveyard. So which you can see here on the as the blue points. Basically, two points here are compact objects that then merge to produce a more massive compact object, as indicated by this arrow here. And the entire stellar graveyard after the O4A gravitational wave data release in September last year. And for comparison, you also see the electromagnetic black holes from X-ray binary observations, and electromagnetic neutron stars as well. And so they span quite a range in masses of the compact remnants. And what we have looked at, we've looked at their chirp mass distribution. So the chirp mass distribution of merging binary black holes. And so the chirp mass is defined as from the masses of the two black holes, such that as you can see summarized on as this formula. And this is what we plot here, basically the source frame chirp mass after we calculate the different selection biases due to the sensitivity of the instruments, and also the volume constraint, and compared to the so what we do here is the following. So we have the chirp mass distribution of the observations. This is the white curve here. And we make binary population synthesis predictions with different supernova models to make the predictions of the binary black hole mergers and the resulting chirp mass spectrum and its histogram distribution. And something that we find is that the alternative supernova models, such as Fryer 2012 rapid delayed, Fryer et al. 2020, Mandel and Müller, they all overpredict the rates of first of all the rates of binary black hole mergers, and also do not reproduce their this trimodal feature peak trough structure in their distribution, whereas our model comes close to it. Right, it's not perfect, as you can see, but it mimics more the actual data. And there's quite a simple explanation for this, as you can see here. So the main explanation is a bimodal black hole mass distribution. Because of this split into these segments of black hole formation, there is also a split in black hole masses, which we denote here as low mass and high mass black holes. So these are basically the all black holes that we get from the population synthesis, and they dissect into these peaked structures. And there's also the chemically homogeneous evolution channel. And now, if you look at the black holes in binary black hole mergers, then they have an even more strongly pronounced peak here coming from the low mass black holes, and this structure. Basically, so this bimodality is preserved. So there's a gap in black hole masses in between about 12 and 16 solar masses that we predict. So there are no merging binary black holes having masses in between 11 and 16. That's the prediction. And when we compute the chirp masses, then we basically reproduce it by mergers of low mass plus low mass black holes. This is the blue shaded here. The pink shaded or the purple shaded peak here comes from the low mass plus high mass black hole mergers, whereas here this additional structure here comes from the high mass plus high mass merger. So basically, quite a simple explanation for this complex structure, just by combining in the three different ways the two segments of black hole formation. And when it comes to the observations, then these peaks get tilted around because there's an observational bias towards the higher chirp masses, and so this peak is more pronounced than the first peak. So that's what we get. And so this, what you have seen so far, is for a particular binary population synthesis configuration, but there's also a variation that we explored of the stellar and binary physics, and also to the cosmic star formation history. And that changes the distribution of predicted chirp masses. And what we get is that despite a variation of these binary physics and cosmic star formation, the other supernova models cannot really reproduce the chirp mass structure. So basically, as we argue, they are ruled out by the observation. That's our argument. Whereas our model, it basically can basically reproduce the features except for the low mass black holes. So we conclude that our modeling underpredicts the formation of low mass black holes. Even when star formation history is varied, we cannot get the low mass black holes. And yeah, basically this is it. I have more slides, and if in case there are questions, other than that, apart from that, I would like to thank for your attention and look forward to your questions in our discussions.
Thank you very much. That was really, really interesting and really nice talk. If there are any questions, we'll be happy to take them. Just let me know.
Thank you.
While in the meantime, I have several actually. So if you don't mind. So
Yeah.
for example, you mentioned that, I mean, from the earlier plots, there are different regions for the main sequence mass, let's say, of a star to actually end up being a neutron star, I guess.
Yeah.
That would obviously result in, a bit massive neutron stars and so on. But I was wondering whether if there is anything other than the mass of the neutron star we can say about the outcome? Like, would it affect the magnetic field strength of the neutron star, or would it have any other, apart from the mass of the neutron star itself, would it have any other observational signatures that we can ask? Like, I don't know, the magnetic field strength just
Yeah,
came up.
yeah. Okay, so let me come back to to this basic plot of where we make the predictions. Okay, so
Yeah.
here we discriminate the single stars, and by this we denote stars that retain a hydrogen-rich envelope at the time of explosion. Um, and the case B donors, they are depleted of the hydrogen-rich envelope. And so an immediate observational basically the distinction or based on this classification is that these stars they would produce type 2p supernovae
Hmm.
from this region, whereas the case B donors they would produce either um, type 2b or type 1b or type 1c supernovae. And this is what we also have here on this slide here. So the type 2p supernovae produced by stars coming from exploding in this region or in this region
Hmm.
from the single star progenitors, whereas for the case B donors, you would get the type 2b, 1b supernovae, or even type 1c for the most massive ones, which where the mass loss is so strong that at high metallicities, basically, that even the helium-rich layers are depleted. Um, so this is that. So the magnetic fields, I must say, we did not include in these simulations. So these are not part of these are not considered in the actual semi-analytical model, which basically is the base for this the entire parameterization. But that said, the magnetic fields they are very important here at the highest mass range because we do not consider here the magnetorotational supernova mechanism, which is a different one than from the neutrino-driven one. And this is relevant for the high, very strongly rotating cores that, due to the dynamo mechanism, then develop amplify the seed magnetic fields that then help the explosion of the massive stars and then can lead to a type 1 CBL supernovae, for instance, right? So this is would be a manifestation of a magnetic fields being involved in the explosion mechanism, which would you would expect to take place here at the various highest CO core masses. So basically, what is colored here as black
Yeah,
would instead lead to an explosion.
I
So
see.
this is the idea, but we do not really consider that, and probably the parameter space for these phenomena is not high. But something I would also like to mention, in case there's also interest in the zero H sequence mass based parameterization of the model outcomes, is that this is something that I have also in place in ongoing work, where instead of the carbon oxygen core mass for the single stars, I also have the parameterization of final phase and remnant types um, as a function of zero stream sequence mass, but just for the single stars and solar metallicity. So if there is, for example, observers who perform SAD fitting or so and
Yeah,
obtain zero stream sequence masses, and they want to guess the final fate of the star. So this is something that could be used for instance. Okay, so I hope perhaps it
I
was a bit much to your question, but I hope it.
thanks, thanks. I was just trying to find an easy way to separate the stars that would form magnetars maybe and the normal neutron stars, and stuff, but
Yeah.
it's not it's not that easy, right?
Yeah.
Uh,
So the magnetar, one other channel for forming them is also the stellar merger, right? So
oh,
where
yeah.
this,
Yeah. Well, that
yeah,
would be,
yeah,
yeah,
yeah. So
interesting.
this is something that we do not really consider here, the neutron star based, yeah.
Another quick question. For the lower mass black holes that where you were saying that your model and the predict observed rates would not be matching very well, would
Mhm.
it be that because I remember that there is an issue, kind of an issue, open issue of within our galaxy, when you look at X-ray binaries with black hole binaries and so on,
Mhm.
there is no uh, low mass black hole binaries so much, apparently, as
Right.
much as expected, you would expect. Would that be some sort of a same thing, or would there be, I was more wondering, would there be an observational effect where we do not really see them? I don't know if they are not in the binaries or whatever, but would there be an observational issue or selection effect that we are missing some of the lower mass black holes?
Mm. So yeah, this is an interesting point to make the comparison to the so-called electromagnetic black holes, right? And
Yeah.
there's this I think there's this paper by Özel et al. From
Yeah,
2020,
I remember that.
from 2010, sorry,
Yeah.
where just by looking at the distribution of the black holes in X-ray binaries, there is this gap in between 2 and 5. That was initially the case. By now, it is actually filled by some stars, as you
Hmm.
can see from this plot.
Hmm.
So in between 2 and 5, there are these candidates. They're yeah, they are currently predicted to be black holes, not neutron stars,
Hmm.
although it's hard to tell really.
Yeah.
Right? Depending on the neutron star equation of state and so on, rotation involved. But I think in our case, we cannot really, we can say quite clearly that this chirp mass here cannot involve the neutron stars.
I see.
So we do not have any observational bias that would so we basically observe the
I
low mass mergers.
I see. Okay.
So it cannot be an observational bias due to which we basically would have. So we do believe the observed curve, and I think we are quite certain that we are missing out some of
Some.
the
I see.
low mass black holes. Yeah.
I see. All right. Thank you very
Mm.
much. I don't know. So. Are there any other questions within the audience? You could just type it in the chat or say it out loud, I guess. Uh, but if not, I would like to thank you very much, Kiril, one more time.
Mm.
This also made our last talk this year. So thanks to all of our speakers previously speaking here as well. Thank you very much, and hope to see you next time. I guess maybe another wedding or whatever. We are here
Great.
always
Yeah.
waiting for you. Thank you very much.
Perfect. Yeah. If there is also interest in applying the zero issue sequence mask based model, then also let me know, and
Oh,
we can easily follow up on this. And yeah.
all right,
Okay.
sure. Yeah,
Thanks.
definitely. Thank you very
Thanks very
much.
much. Yeah.
Thanks. Bye.
Bye bye.